So before we start the formal part of the course, I would like to discuss a few examples to motivate the kind of problems we'll be looking at. So we start with the problem of air travel. So we have an airline, Barbet Airlines, which serves several cities in the country. And of course, although it serves several cities, it doesn't really connect all these cities directly. Only some of the cities are connected by direct flights. And for other pairs of cities, you have to take a hopping flight. You have to go via an intermediate city. So our first goal may be to compute every pair of cities which are actually connected by this network served by this airline. So how do we find out all pairs of cities A, B such that A and B are connected by a sequence of flights? So first we need to look at the network. So this is a typical way that we might find the network. For example, if we open the in-flight magazine of an airline, you find a route map and it's written like this. You have a physical map of the country and you have the cities which are served marked out. There are about 10 cities, Delhi, Varanasi, Ahmedabad down to Trivandrum in the south. And you have some arrows indicating the flights. Now in some of these flights are in one direction. You can go from Delhi to Varanasi, but you can't come back directly to Delhi. You must go to Ahmedabad and then come back. So this is quite common if you look at airline schedules in airlines. You will find that you have these kind of triangular routes where you go around a triangle and you can't go back directly without hopping in between. Some pairs of important cities, like in this case Mumbai and Delhi, might be connected by flights in both directions, or even Mumbai and Calcutta. Okay, and so now we have these 10 cities, and we want to know, is it really possible to go from, say, Varanasi to Trivandrum, or is it not possible? Is it possible to go from Hyderabad to Delhi, or it's not possible? So our first step is to model this problem in such a way that we retain the essential details which are relevant to solving the problem and get rid of all the unnecessary details. Okay? So this case, what we really would like to know is the structure of this network, right? So the map itself is not relevant. We just need to know how many cities are there which are on the network and how are they connected by flights. So the picture below, which has these gray circles and arrows, represents this network. The cities are the gray circles and the flights are the arrows. The arrowheads indicate the direction. So if there's an arrowhead in one direction, it's a one-directional flight. If there's an arrowhead at both ends, it means it's a bidirectional flight. The actual names of the cities are not so relevant. We can call them 1, 2, 3, 4, 5 or A, B, C, D, E or whatever, okay, and solve the problem. So this kind of a picture is called a graph. We will study graphs more formally when we come to this module in our course, but a graph is just a picture of this kind. So it has some nodes, these dots and edges. So now one nice thing about moving to this abstract level is that the actual picture can be distorted without changing its meaning. So we can move, for instance, if you look at this city here, right, we can move it to the right and it doesn't make any difference in terms of solving the problem. Or we could simplify the picture by moving, for instance, this edge outside, right, so that we get no crossing edges. And this is again the same picture, though it looks quite different from the picture that we started with. This is again the same network. Now in some situations it is useful to realize that the graph that we have looks like this, that there are no crossing edges. Technically such a graph is called a planar graph. It can be drawn on a flat piece of paper without any edges crossing. For planar graphs, we might have better algorithms than for arbitrary graphs. Now what do you want to do with such a graph? Okay. So in this case, we want to compute what we call a path. That is a sequence of edges going from one city to another city, where of course the direction must be correct. So you can't go backwards across an edge which is flying from A to B. You cannot take the same flight from B to A unless there is another flight. So our first question is, how do we take this picture and put it into form that we can manipulate using a program or an algorithm? So we need a suitable data structure in order to represent this graph. Now, given the way we represent the graph, we need to manipulate it to answer the question at hand. In this case, connectivity. How do we go from A to B? Or can we go from A to B? Or which all cities B can I reach from A? So how do we design such a data structure, an algorithm, given the way we have represented the cities in this graph? Does it depend on the representation? Are there multiple representations, some of which give us more or less efficient algorithms? These are all questions that we need to answer before we can decide on whether we have got the best solution at hand. Now, in terms of efficiency, we have to look at what are the things that determine the complexity of the problem. It's fairly obvious in this particular case that if we have more cities, the problem is more complicated. So the number of cities, which we can call n, is certainly one parameter which determines how complicated the algorithm is going to be, or not how complicated the algorithm is going to be, or rather how long it is going to take to run. The other question which determines how complex the network is how many direct flights there are. Obviously, if there are fewer flights, there are fewer places which can be connected, and we have to explore fewer possibilities. So from this, it follows that computing the paths depends on both n and f. So we will not have an algorithm which will always take, say, 20 steps. It will have to depend on some number of steps depending on n and f. Now, what is this dependency? How does it grow? If n doubles, does our algorithm take 2 times more time? Does it take 4 times more time? Okay, if n goes by a factor of 10, does it take 10 times more or 100 times more time? The other question related to this is, given this dependency on n and f, what realistic size of networks can we handle? Okay, if the airline grows to 20 flights, will we still be able to give our answer in a reasonable time? Remember that this kind of an answer is typically required when somebody is making an online booking or something, and you want to reply in a few seconds, right? It's not enough to come back after an hour and say, yes, there is a flight from Trivandrum to Calcutta. So what is the limit of our efficiency? Can we scale this algorithm to cover airlines, multiple airlines? So we have a website which actually says across all airlines, I can take you from place A to place B. That depends on how large a value of n and f we can handle. And then, of course, the problem that we have looked at is a very simple problem. Can I get from A to B? But very often it's not good enough to get from A to B. You want to get from A to B within some reasonable time frame. For instance, it's not usually acceptable to break journey overnight on air travel. Okay? At the same time, you also don't want to spend more than a certain amount of time waiting in between flights. So there are only some connections, although they may be, theoretically there may be connections, only some of them may actually be feasible. So now our problem becomes a little more constrained. So we don't just want to look at connected paths from A to B, but connected paths A to B which meet some additional constraints in terms of timing and other things. Right? So can we solve this problem with the same approach that we solve the simpler problem? Or do we need to take a radically different approach? Or do we need more information in order to decide how to solve the problem? Suppose, as we would expect, each sector on this thing has a cost. As a passenger, the cost would be the price of the ticket. So if you are trying to compute the best way to go from A to B, your motivation might be to choose the cheapest route in terms of the ticket cost. Of course, cost is not only money, cost could be time as well. You might also want the quickest route from A to B, the one which involves the least waiting. So it depends on what your priority is. Are you urgently required somewhere, in which case you don't mind paying more? Or are you going on a vacation with the family, in which case you have a relaxed time schedule, but you want to make sure you get value for money? From the airline's point of view, there may be other questions. Periodically, aircraft have to be brought down for a day for maintenance. Now, you don't want to have so many aircraft that you keep all the routes flying and wastefully keep planes unused. At the same time, if you keep too few planes, then when you bring an aircraft down for maintenance, you have to sacrifice some routes. Now, which routes should you sacrifice so that you ensure that the connectivity of the network remains the same? If you could earlier go from Trivandrum to Calcutta during a maintenance shutdown, you should still be able to go from Trivandrum to Calcutta, maybe by a different route. So this is a problem to be addressed by the airline staff, whereas the cheapest route might be a problem to be addressed by the customers. So there are very many different kinds of questions you can ask about this basic this air network that we have described using a graph. And we will see answers to some of these problems in this course.